Okay, so let us begin with the homework problem. Right, so last time what we did is we show the monotonicity of a sequence and boundedness of the sequence, and then apply monotone convergence theorem to prove the convergence of the sequence. And then by using the property of the sequence, or by using the way the sequence is defined, we are able to derive the limit of the sequence. That is what we did last time. So this example is again a homework problem. It's again a similar problem, right? So you have initial value t1, and then tn plus 1 is defined as tn plus 7 square root, right? So this is obviously, you can see the numbers are increasing because square root of 7, and then square root of 14, and then square root of so on, so on, so on, so on. Then not square root of 14, square root of 7 plus 7, and then square root of 7 plus 7, and so on. So you can see that it is an increasing sequence, and if it is an increasing sequence, then you can verify the bound, right? So you can prove that it is bounded below by a certain number, and then you can say that it is convergence because of the monotone convergence theorem. And then finally you can find the limit of the sequence, right? So, and that limit is basically the root of the equation x squared minus x minus 7. So this you can verify. Right. So now what we are going to do is we are going to go to new concept called subsequences. Right. So you have learned about sequence, right? So then what you do is, say you have a sequence, right? Say 1, 2, 3, 4, 5, and you have a sequence like this, right? So this basically is the sequence of n, right? So the sequence of n, you can write it like this. So from this, you can pick a small piece, right? 1, 3, 5, 7, and so on, right? So this is a sequence of arcs, right? Or you can pick something else like 2, 4, 6, 8, and so on, right? Or you can pick 1, 5, 9, and so on, some kind of a pattern, right? Or you can pick 1, 10, 15, 25, and so on. So you can always get a sequence from within a sequence, right? So once a sequence is given, then you can always get a sequence within the sequence. And that procedure, or that sequence within the sequence, is called subsequence. So that is how you define subsequence. And then what we are going to do is we are going to use the properties of subsequences to see the properties of the sequences as well. And so that is what we are going to study in this section. Okay, so first we will define subsequence. Definition. Okay, so if you get a subsequence of indexes, right? So strictly increasing sequence of indexes, then you can say that the sequence with the strictly increasing index, which is a subset of the natural numbers, is called subsequence. Right? So this is one example. Right? Similarly, you can have several examples. Right? So if you have 1 upon n sequence, then one have 1/3 are the numbers, and then you can have this kind of subsequences as well. Okay, so the only thing is you cannot change the order from the sequence, right? So if it is a sequence of 1 upon n, then you know this is 1 half, 1/3, and so on, right? So the subsequences can be 1 half, 1/4, and so on, or 1/3, 1/5, and so on, and so many ways you can define the subsequence. Right? So only thing you have to be careful is you cannot change the order from the sequence, right? So if you have a sequence like 1/2, 1/3, 1/4, 1/5, and like that. You cannot say 1/3, 1/2, then 1/5, then 1/7. This is a subsequence. You cannot say, right? So that cannot be a subsequence because the order in which the values are placed in the sequence is should be same in the subsequence as well, right? So you cannot just change the orders and pick arbitrary values and then make a subsequence. That is not possible, right? So you may have to make sure that the order is same, right, from the original sequence or as in the original sequence, right? So now we are going to see a remark here. Okay, we are going to see a remark here. Okay, so what we are writing here in the remark is we are showing that the sub-index which is associated with the subsequence is always greater or equal to the corresponding index in the sequence, right? So let me first show you an example of what we are saying, and then we will try to see the proof. The proof is not hard. It is just basic mathematical induction. So let us say this sequence, right? The sequence n. So you know x1 is 1, x2 is 2, x3 is 3, x4 is 4, x5 is 5, x6 is 6, and you keep on writing the sequence like this, right? So if you have xn as n, right? If your xn is equal to n, then your x1 is 1, x2 is 2, x3 is 3, and so on. Right? So now you remember, you pick a subsequence, right? So that is xnr is the index now, right? So xnr is the index now, right? So right, so these are the subsequence, right? Because xn1, xn2, xn3, xn4, like that, you are going to define the subsequence, right? Or x1, 1, x1, 2, and so on. Right? So that's fine. So now let's say I am picking the even numbers, right? So even numbers. So I will start with 2. I'll start with 4. I'll start with 6. And I will continue like this, right? But in the original sequence, you can say that this is your x2, right? Right, so this is your x2, and this is your x4, this is your x6, right? So that is what you have in your original sequence, right? So you can see that actually this number is this, right? So this 2 is larger than this 1. So this index 2 is bigger than or equal to the index here at 1. 4 is bigger than or equal to the index here 2. 6 is bigger than or equal to the index 3, right? So sometimes if I take odd numbers, right, then I will have equality because xn1 and x1 are same. So in this case, you have equality as well. So that is what we are saying here. The index in the subsequence is always greater or equal to the corresponding index in the sequence. So that you can prove by induction, right? So the idea is this, roughly the idea is this. The first element in the sequence is greater or equal to the first element in the, or the first index of the first element in the, the first element, index of the first element in the subsequence is the corresponding index of the first element in the subsequence, which is 2 in the original sequence, is greater or equal to the corresponding index of the element in the original sequence, right? So here you pick the second element as the first element, so that 2 is greater than 1. Now you take the fourth element as the second element, so 4 is greater than 2. You take sixth element as the third element, so 6 is greater than 3. Here, if you pick odd number, you take first element as the first element, so 1 is equal to 1. Next, you will take third element as the second element, right? Right? xn2 is 3, that is x3. So next, you take third element as a second element, so 3 is greater than 2. Right? So that is what we are proving here. Right? So that is not a big deal because by induction, you know that first element is always greater or equal to 1. Right? So that is obvious. Here, if it is equal to 1, or it can be greater than 1. So greater or equal to 1. It is clear. Now, to prove this by mathematical induction, you assume that it is true for some P. So NP is greater or equal to P. Right? But you know, NP is a strictly increasing sequence. So NP plus 1 is strictly greater than NP. But NP is greater or equal to P. So NP plus 1 is strictly greater than P. Right? So that you have. But you know, you have to have NP plus 1 is greater or equal to P plus 1. So for that, you use the idea you study in chapter 1. Right? So when you talk about natural numbers or integers. Right? So you see that P is a natural number. So if P is 5, then P plus 1 is 6. Right? At the same time, NP plus 1 is also a natural number. So suppose if P is 5, NP plus 1 is 6 or more, right? Because NP plus 1 is a natural number, P is a natural number. So NP plus 1 should be at least 1 more than P, right? That is the only possibility because it is natural number. So then NP plus 1 is greater or equal to P plus 1. So by mathematical induction, you can say that the sequence NP plus 1, NR plus 1 is always greater than NR. Right? So that is the reason you are doing this is to show that if the sequence converges, then you can always take when you take the limit of the sequence, you can always take the limit of the subsequence as well, right? So right, so therefore by induction for all natural numbers, NR is greater or equal to R. So if you take R goes to infinity, then automatically NR goes to infinity. So this says if you can take the limit of a sequence as n goes to infinity, you can always take the limit of the subsequence as well. Right? Because the purpose of defining the subsequence is basically to understand the limit little bit more. Right? So that is why we use that. So now comes the first result. Right? The first result says if the sequence converges to a limit, then the subsequence will also converge to the same limit. Right? So I will write that as a theorem. Okay, so if xn goes to a limit L, then we can show that xnr, which is a subsequence, and that will also converge to the same limit, right? So it will not go to some other limit, it will go to the same limit, right? So we shall prove this. You notice that we have a definition for limit, so we will write it down first. Okay. Okay, so this is the definition we write for limit. For every epsilon positive, there exists a natural number n such that xn minus L absolute value is less than epsilon for all n greater than n. Right? So now you have to do it for a subsequence. Right? So now you know that the index of the subsequence is r. Right? So small r. That is what you have. So let me do. Right, so let us define a capital R as n, right? Because I just changed the notation because you know the subindex of or index of the subsequence is nr. So I'm using r. So then for every r greater than r, right? R is greater than. Then for every r greater than r, you know that small r is greater than n. Right? Small r is greater than n because r is equal to n, right? So that's not a big thing. But by the remark which I just proved, but I have this nr is greater or equal to r for all r belongs to natural number. That's the remark I proved. Right? So for every r greater than r, nr is greater than r, but r is greater than n. So nr is strictly greater than n. So we know that, right? So nr is greater than n. So then we can apply this nr in the limit results, right? Thus, for every epsilon positive, now there exists n belongs to n, but you choose n is equal to r. So I can say there exists capital R belongs to natural number such that, right, n for all n greater than n, xn minus l is less than epsilon, but nr is also greater than n, so nr will work here. Right? So for all r greater than r, right? So xn r minus l is less than epsilon for all r greater than n, right? So OR here. So this is the definition for the limit of the subsequence, right? Exactly same as the limit for the sequence. So this says limit of r goes to infinity, x n r equal to n. So we can see that limit of the sequence as well as limit of the subsequence are same. Right? So this is one of the useful results because if in case you cannot find the limit of a sequence, right? What you can do is you can always get a subsequence and then get the limit as well, right? So if the subsequence goes to a limit, then you can see the limit of the sequence as well. So we are going to see a couple of examples, right? So first, I will write the examples and then try to do it one by one based on the time we have. Right, so we have two results. Right, so xn, an is the sequence, a to the power n will converge to 0 if the value a is in between 0 and 1. And then the second one, for a number larger than 1, c to the power 1 upon n is 1. Right? So we shall do both the results. So first I will do the first one, and then depend on time, we can leave the second one as a homework or a right. So here, what I am going to do is I am going to use all the results I have learned already, right? So I know about increasing sequence, I know about boundedness, I know about monotone convergence theorem. Now I know about subsequence as well. So I'm going to use all of them to verify this result. Right? So let xn is equal to a to the power n. Right? Then xn plus 1 is a to the power n plus 1, right? A to the power n plus 1. So that is clearly less than n. Right? Right? Because remember a is the number less than 1. Right? So if it is larger than 1, an plus 1 is greater than an, right? But if it is less than 1, then you know, right? So 1 upon 2 to the power 3 and 1 upon 2 to the power 2, you know which one is large, right? So 1 upon 2 to the power 3 is smaller than 1 upon 2 to the power 2, right? Same argument here. An plus 1 is strictly less than an, which is xn. So clearly, you can see that xn is a decreasing sequence. It is strictly decreasing, right? At the same time, because 1, right, a is between 0 and 1. So if a is between 0 and 1, a to the power n will also be between 0 and 1, right? So half to the power, whatever power is always less than 1. And at the same time, it will be always greater than 0. Right? So that is how. So this is obvious. So you can see that. So clearly, bounded and monotone. Right? So xn is bounded and monotone. So convergence. Okay, so xn converges. Right. So now what we are going to do is we want to find the limit, because we proved that by using monotone convergence theorem, the sequence a to the power n is converging. But we still did not find the limit. So we have to find the limit. So we are going to use the subsequence property to verify the results, or verify the limit of the sequence. Right? So that is what we are going to do. Right. Okay, let me say L is the limit of the sequence, right? So let me say L is the limit of the sequence, which you don't know, you have to find, and you have to show that that should be equal to 0, right? So right? So x2n is a subsequence of xn, right? Because you know this sequence is a squared, a cubed, a4, a5, a6, and so on, right? x2n is a to the power 2n, right? So xn is a to the power n, and this is this. So if you take x2n, that is a to the power 2n. So that is going to be a squared, a4, a6, and so on. Right? So that is obviously a subsequence which you can easily see. Right? So if this is a subsequence, the limit of this sequence is L, right? Because you just prove the sequence of the limit and then sequence subsequence limit of the subsequence is L. So this means limit of n goes to infinity, a to the power 2n is equal to L. But a to the power 2n is limit of n goes to infinity, a to the power n quantity square, right? So you know that a to the power 2n is a to the power n quantity square. So this is L, but you know limit of this is also L, right? A to the power n is L, so that is L square. So what you get is L is equal to L square, and because limit of a to the power 2n is L, but at the same time limit of a to the power 2n is limit of an squared, so that is L square, because L is the limit, L squared is the other limit. Again we studied, right? So if xn is the sequence goes to L and yn is a sequence goes to M, then xn yn goes to Lm. So an is a sequence goes to L, another an is a sequence goes to L, so it is an times an, L times L, so L square, right? So we use all the results we studied so far. So now you can simplify this, right? So if you simplify this, you know L squared minus L is equal to 0. So that gives you L is equal to 0, 1. So you have two values for L. You have 0, at the same time you have 1. Right? But you know you want to show L is equal to 0. So you have to eliminate 1. You have to show that 1 is not the correct answer. So we will do it by contradiction. If you take L is equal to 1, right? Right? Monotone convergence theorem. In monotone convergence theorem, you show that you prove that if xn is a decreasing sequence and bounded below, then the limit of the sequence is the infimum of the sequence. Right? Limit and infimum are same. So here L is the limit, so it should be the infimum of the sequence as well. Right? So if it is infimum, then clearly you know xn is greater or equal to L for all n, because infimum is the smallest, is smaller than all the values, because infimum is basically a lower bound. Right? So all the components must be greater or equal to L. So you have xn is greater or equal to 1. Right? If L is the limit and it is equal to 1, right, xn is a decreasing sequence. So L limit should be infimum. So all the components must be greater or equal to the limit. So all the components xn must be greater or equal to 1. Right? But what you have here, xn should be strictly less than 1. Right? So this is Right? So because xn is in between 0 and 1 for all n, xn cannot be greater or equal to 1. So that is a contradiction. So L cannot be 1. And if L cannot be 1, then the other choice, L should be 0. So that is what we wanted to show. We wanted to show that the limit is 0. So here in this example, you can see that we use all the results we studied so far, right? So we show monotone convergence theorem. We use the results of limit. We use the results on limit of product of sequences, and then we use infimum property of limit, right? And then we get the contradiction. And so this is an example of how you can use all your results you studied in one exercise, right? So I will leave the second exercise as a homework for you to work on, and in the next class, that is tomorrow, we will continue working on some more properties of subsequence, right? So we will see the rest in tomorrow class. The notes are already uploaded in the LMS, so you should be able to see it and download it.